force position graphs. So this is typically a side note when you're studying physics, and most of the time you might not even run into this unless you have a pretty good teacher who's going to be teaching you this particular concept. So it's the introduction of the fact that when you're calculating work, so as you can see here, so if you have an object, you know that work is really defined by the force vector that you have in the direction of your displacement vector. So now your displacement vector, is in one direction, and you may be lucky enough that, of course, your force vector is in exactly the same direction, but it may not be, so it might be at an angle with regards to your displacement vector. So you can see that angle, so I've designated it by a theta, and you have your, at least your magnitude in the same direction, which is just your magnitude of the force times cos of the angle. Now, that isn't anything new, and my assumption is that you're familiar with that. So I can put up a link up above there, okay, if you want more information on how to do that and how to work with that. Now, the key thing here is that I want to point out is that typically we will assume that this force vector that you have is constant. So it is exactly the same, okay, in terms of its magnitude and angle that you have in the direction, okay, as long as you're calculating the work that has been done. So this equation that you have makes a key assumption here that this force is basically constant, okay, on that displacement that carries out. Now, when it is constant, then it's not very difficult to try to calculate this. Now, this is, of course, dependent also on this cos theta, so the angle that you have. And here, if you wanted to draw this force and position vector, so as you can see there, so I have my position here, right, which we can calculate what the displacement is, which is what we need. Okay, so that would be from your initial to your final, whatever that displacement is, you can calculate and find that out. And then I have labeled on the y-axis, you can see there, you have f cos theta. And typically, so what will happen is, so instead of, writing this, when you're seeing these force position vectors, typically they'll just simply say f, and the assumption is that f is in the direction of your displacement, right? So they've already calculated that component. So I'm going to just leave it, okay, as it originally was. And what this means is that if you're going to be calculating through and you have some constant vector, so let's say, for the duration, okay, of the displacement, maybe the actual force that you had, maybe this is what it was. So you can see there that it's basically 30 newtons. And what this is saying is that you have, 30 newtons, okay, in terms of its magnitude, that is being applied during the actual displacement, okay, that is carried out. So let's say, that this was the entire displacement that we would carry out in here. Okay, I'm going to just change this so that it kind of aligns in there. Okay, so from there, so that 30 newtons was present. Now, in order to calculate this, well, if that 30 newtons is in the direction of the displacement, then all you would do is you would just simply multiply the two together. So you would take and you would have your 30 newtons, you would multiply it by the displacement that it took place. So notice that if, let's say, if this was in meters right here, and I'm going to just assume, let's assume that this is 1 meter, 2 meters, 3 meters, 4 meters, let's say 5 meters. So this right here, so this would have been 4.5 meters. So I can multiply this and I would obtain, so I can take my 30, multiply it by 4.5, and I get 135. And this would have been Newton meters, or 135 joules. So there we have it, and that's how you would calculate your work. So not a big deal within this. But what I want to be able to point out here for you, if you do plot this, right, because you might say, well, why did you even plot this? Why couldn't you just calculate it? And that is true. That's what you most of the time will do. But when you plot it throughout, then what it turns out, if you do have a force and a position graph like you do here, then you will notice that the work is actually the area under, okay, this particular curve, right, or this line for us. So if you calculate the area under this curve, then indeed, well, the area is, so you would calculate, all right, so my area, it's a rectangle. So this is 4.5, and then the actual height, okay, of that rectangle is 30. So the entire area of this is indeed nothing else but simply equal to, 30 newtons times 4.5, which is give us the 135 joules. And with that note, now you can start really thinking about any forces that are applied. Because the displacement that you have, okay, is going to be, okay, whatever it is. But the forces that you apply, they may not always be constant. So it doesn't mean that they're always going to be constant. They might indeed be changing, okay, in some way. So, you can draw this out and you can have something different. So for instance, if I would draw this out, and I'm going to just repeat this right here, and let's say all the things are aligning, so in terms of the scale. Now, what if you had, so instead of the force being constant, maybe it was, okay, all the way out in here, and it was changing. So as you can see here, if this was the force in the direction, now it's still being positive. So let's say this is 10, 20, this is still 30. Now all of a sudden, you might scratch your head and you might say, okay, well, how do I calculate the work now? Because it's not constant force that is being applied through the entire displacement. So it looks like, so within here, so I still have a displacement, okay, so within here, so this is 4.5 meters, okay, if I'm aligning it, so all the way from there to here, so that's all great, but I don't have a constant force, okay, which I could just calculate and multiply 30 times that. So what would I do in order to find it? Well, so this means that at every single, different points in time, you have a different force that's applied. So it turns out that indeed, in order to find the total work, it will be just the area that is covered in this force position graph. And that is really cool. Now, these are really the only two, so in terms of rectangular and triangular, those are the ones that you're probably going to be running into when you're talking about kind of your initial foundation of physics classes, so maybe grade 11 or your first year physics courses. But if you get on into further, these particular forces, they don't have to be straight lines or triangular. They can be anything. And then it comes down to, can I find the area under the curve between the force and the distance? And that area under here, so whatever area this is, would actually be the amount of work that has been done, right? Or the energy that has been transferred or taken away from the object. So that is really cool. So in this case, well, triangles, hopefully we're familiar with. So remember that for a triangle, the area under the curve is just 1/2 times 30 times 4.5 in this case. Well, so we knew that that was 135 for here. So it's 1/2 of 135 joules, right? And now you can take that, divided by 2, and you're going to get that the area was 67.5 joules. That is really neat. So that's how you can calculate, and this is what I wanted to point out in this video, that if you want to be able to find out what the work is when your force is not constant, right? Not when it's just a straight line on your position force graph, okay? If it's possibly maybe at an angle of some kind, okay? Or, creates a triangle, then don't forget that the work is equivalent to the area under the curve. And that indeed is the case, and it still does come from the definition of work, just a more general definition of work, when your forces are not constant. So with that, you can take a look at something which is kind of a little bit crazy like this. When someone tells you that, all right, so here's your position, right? So you have your position actual. Okay, so that's your position right there. So as you're moving along in here, you notice that, well, for the first stretch, okay, right there, it looks like the force was constant. Notice this is west, so this is all in the same direction. But now all of a sudden the force has changed. So this is the actual now new area. And now notice that it actually goes negative. So that means that the force is actually in the opposite direction. So it's either in the direction of movement, west, or in the opposite direction, okay, which is going to be, I guess, east, okay, or just negative west. So now, how would you calculate the work in this case? So you can calculate the work in this case by dividing this into several regions. So here's your first region. So that work, okay, so work number 1, so this is the area that I have right here, okay, is going to be, so notice 10, 20, 30, so this is going to be 30 newtons, and then 1, 2, 3, 4, 5, 6 meters. Okay, and this is coming from, so here's my legend over here, so you can map them on. So 1 centimeter equals 1 meter on the displacement side, and 1 centimeter equals 10 newtons. So within here, so this is going to be 100, I guess, 80 joules. Now, in the second portion, so this is going to be the second portion over here. Okay, so I'll label it over there. So that's that. Now notice that the force is not constant. It's changing, right? So it's 30 newtons here, and then it goes down, 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 all the way into basically 0. Okay, and then you have the displacement that is carried out. So that's going to be a triangle. So that's that. Now this is going to be 30 newtons is the height times, this is 1, 2, 3. So it's going to be 3 meters. So 30 times 3 is 90, and that's half of that, which is going to be 45 joules. So there you have that. Now you can continue that. So now this is going to be your third one. Okay, so this is work number 3, but notice that now it's negative. So that means the force is in the opposite direction, okay, of the displacement. So we're going to have a negative work in here. So I'm going to just label this, okay, as negative, and this is going to be 1, 2, 3. So notice again, it's a triangle. So this is going to be 30, and this is only 1 meter, okay, that this moves. So that's 30. So this equals to negative 15 joules. That would have been the work done right there. And then lastly, you can do your last one right there. So that's going to be this piece. Very easy. Okay, so this is just a rectangle. So this is work number 4. So this is also negative. And this is nothing else but simply, negative 30 newtons multiplied by 1, 2, 3, 4. So 4 meters, or just simply 120 joules. And there you have it. Now, if you want to know what the total work is over that whole duration, then you're going to have to add all of them up. So that's going to be 180, and this is going to be plus 45, minus 15, and then minus 120. And there you have it. So now if you do all of this, I don't want to do it in my head, although I probably should. Okay, so I'm just getting a little bit lazy here. So 15 and then minus 120. So that's only 90 joules. Now notice it is positive, right? Work in this case. So this would have been the actual work computed, and you can find it through doing the area under the position and force graph. All right. So now in your position force graphs that you have, typically when you draw this on the earlier side, you notice that you either will have the force positive or negative, meaning that it's either in the direction of your displacement or in the opposite direction. Those are really the only two that you have. If you have something different where the angle, okay, now starts to sway on your force, okay, then you would have to do something a little bit different. You would have to get that component on. So these are just mapping the components of the force in, okay, either the same direction as your position, okay, your displacement is occurring, or in the opposite direction. So that's what you're finding out, okay, in order to do this. So I hope that this is helpful and it gives you a sense, and you now understand and see that indeed you can use force position graphs to calculate the work. And it's not that hard if you're finding just the area under the curve. Thanks for watching. Okay, we'll see you in future videos. Bye, everybody.